All right, we're going to get the talk going.
Okay, thank you very much. Today I'm going to be presenting my topic, which is Meddle. It's a framework for piggyback fuzzing, as well as it's pretty useful for reverse engineering tool development as well. This presentation is not affiliated. First, I'm going to go over a little bit of background. Then I'm going to go into the Meddle framework itself. Then I'm going to go into a few examples of using the framework for several different purposes. One is, the first demo is going to be attacking the open source XRDP server. And then afterwards, we're going to go into dumping the device I/O control messages. And I've written a parser to load the captures into Windows Message Analyzer as well. And if we have time, we're going to...
Can I interrupt momentarily? What's our tradition with first-time speakers?
So that thing that I said wasn't going to happen is happening.
Thank you.
Here, give me that back. You saw nothing.
Okay, sorry about that, guys. So first about myself, I'm visiting out from Vancouver, Canada. I currently work at Microsoft, though the presentation is not affiliated. I originally got into reverse engineering from game hacking. If anyone really cares, probably not. So first I'm going to go over a little bit of background. There are several different types of fuzzing. And some of these overlap with one another. They aren't exactly distinct. Like, for example, file format fuzzing can be PDF or Microsoft Word. Meanwhile, protocol fuzzing could be things like RDP. Application fuzzing could be COM objects or API calls. In some of those cases, you might be looking to, say, escape either a browser sandbox, or it could be for elevation of privilege on the local machine. And web application fuzzing is kind of a different story. It could be Joomla or web applications, or looking for SQL injections. There's quite an array of existing fuzzing tools out there right now. A couple of these worth particular mention, I would say, would be Spike from Immunity is a very popular commercial one from my experience. Another couple worth mentioning would be the Sage from Microsoft is a really fascinating one I'm going to go into a touch of detail on. The I/O control fuzzer by eSage Lab here is also really cool. It's actually running in the Windows driver mode, and it fuzzes all the driver communication coming from actually the driver itself. So that's going to be related to one of our later examples where we're doing a similar thing from user mode. There are quite a few different fuzzing algorithms. These are only a couple of the particular ones I'd say which are worth really good mentions. First, naive protocol fuzzing. Basically, you don't understand anything about the file or the protocol itself. You would just basically randomly modify the data yourself and then load that data in an application, hoping that it would crash. So you don't know anything about the file and format, you don't know anything about the protocol. Protocol-aware fuzzing is where you understand certain things about the protocol. You might know that, say, a certain blob of data represents a Unicode string, for example, maybe a length followed by Unicode string. And then you might try some specifically string-related fuzzing attacks, like you might try a format string. You might try increasing the length of the string to be extremely large as well. So that's more protocol-aware fuzzing, where you have some understanding of the underlying protocol. There's some really cool examples of more advanced algorithms. AutoFuzz implemented a really cool protocol learning approach. You can give it multiple recordings of say client to server communication, and then it builds a model of what it thinks that protocol is, and then it begins fuzzing. So in that case, it might recognize that this is a string, this looks to be the command, and this state leads to that state, and then it might try some protocol specific attacks. Feedback-driven fuzzing is a really interesting approach ran by quite a few people, and it's used by Sage, for example. It's where you basically do runtime tracing of the application that you're fuzzing, and then basically you do controlling of the fuzzed input, and you see how it influences the execution of the application you're fuzzing. And then you can drive certain branches and conditions to be taken to explore deeper, non-accessible code. So that's a really cool approach. In Google, well, the code coverage fuzzing was proven very effective by Google. Google had a big fuzzing project where they fuzzed Adobe Flash. they built a collection of terabytes of Adobe Flash files. Then they rendered each one of those Adobe Flash files in an instrumented version of the Flash binary, and they recorded which code was executed with every one of those Flash files. And then they did a reduction then. They reduced the set of Flash files to the minimum set of Flash files that gets complete code coverage within the Adobe Flash library. So that way they know they're now working with a set of Adobe Flash files which gets as much code coverage as they can get using a small set of files. And then they began using the fuzzing. And that was a really effective approach. I think they discovered over 200 vulnerabilities, I believe, that were reported to Adobe. A very effective approach. So now I'm going to give a quick introduction to a few of the more basic fuzzing algorithms. This is an example of file format fuzzing. True type fonts have been the target of attacks in quite a few cases, like, for example, the Doku vulnerability, with the Doku APT, it exploited a vulnerability in the true type font library because you can actually embed them, say, in a Word document, and it'll be installed when you render the Word document. And it's actually, the true type fonts are actually rendered in the driver in the kernel mode. So they're rendered by win32k.sys. So if you open that document, it gets remote code execution at the kernel level. So it's already really screwed you. For a basic approach to fuzzing true type font, you would actually just take an existing true type font and you'd modify some of the data randomly, creating thousands of variants of that true type font. And then you would install each of those fonts, render each font, and you'd be hoping for, say, a blue screen of death crash dump report as a really simple approach to it. But the true type font is actually really complicated because it's got its own virtual machine language built in there, which they actually used for the exploit. It was rather impressive. An example of simple protocol fuzzing could be an RDP client connecting up to an RDP server, and you're just intercepting the network traffic that's being sent and received, and you're just modifying some of that data in transit, hoping for either the client or server to crash to indicate a vulnerability. So you'd queue up many of the RDP clients connecting up to the server, constantly modifying the data, hoping to reveal a problem. But the problem here is that the later messages in the RDP protocol, they're actually encrypted messages. So it might not have quite the desired effect as you'd like unless you do the fuzzing before the encryption internally within the RDP protocol. So an example how you could target the encrypted messages too is you can do a simple client logic where you actually implement the fuzzing logic before the encryption logic. Then you'd be modifying the traffic as expected in this case now. Or you can actually take a file fuzzing approach to the RDP protocol as well, for example. Luigi Arumia posted a proof of concept which had everyone really worried back in early 2012. And when he posted his proof of concept for the Microsoft RDP vulnerability, his proof of concept was just say netcat to the server and then pipe in this binary I've provided. Do this many times, and then you're going to see the RDP use after free vulnerability. There was a lot of worry surrounding this vulnerability because it was hugely exploitable. Many people have RDP exposed the internet, and had a reliable exploit been actually come out for this, it could have had big implications. But luckily for us, it was a really hard vulnerability to exploit, and I still think there's no publicly known successful exploitation of this vulnerability. API fuzzing, I'm just going to skip it over quickly because I think we don't have enough time for that one. So now I'm going to go into Meddle. So Meddle is an open source framework for vulnerability fuzzing. You're going to be writing all the plugins in IronPython, which is basically the same as Python for most purposes. You can include all the standard modules, you can include regex, you can include OS. As far as I can tell, it's mostly the same. The framework itself is written in C#, but you don't need to touch that unless you want to add additional functionality at the higher level. It's command line based. I put a lot of work into making it support both 32 and 64-bit processes so that most everything you do is independent of whether it's a 32 or 64-bit process. And unfortunately, it's Windows only. I haven't I've only been running this on a 64-bit OS myself, so I know it only works on 64-bit against 32 or 64-bit processes. It still needs to be tested on a 32-bit OS if you're running 32-bit OS, but hopefully there shouldn't be any problems there. So the goal is really to bring a real simplistic environment in order to write some fuzzing attacks, and to be extendable, reproducible, of course, because you want to know what caused the application crash to occur. So the original goal is to go after piggyback fuzzing. So you already have an RDP client, for example, which knows how to communicate with an RDP server. So the idea is to automate many of those RDP clients connecting up to the RDP server to implement the protocol for you. So the framework consists of, you only really have to worry about the iron Python stuff on the right. So it has one controller, which is controlling the attack or measurement. And each controller can have multiple processes. Like you might be running 20 RDP clients in parallel, all connecting up to an RDP server. And each process implements multiple targets. Each target implements a set of hooks. So it might be, you might have one target for winsock send, you might have one target for winsock receive, and you might have a target which adds handle information to the process, for example, as well, for name resolution. How you set up a controller is, the default controller, I have it running right now, is it does a measurement baseline, first of all. So it'll create, say, an RDP client connecting up to the RDP server. And in that process, it'll record, say, 100 messages sent to the server and 3 messages received. So that's instrumented as the baseline, first of all. So in that process, it creates an RDP client, connects to the server. It'll probably wait about 5 or 10 seconds, and then it'll terminate the process. And now you have the measurement of the baseline. Then once it begins carrying out the attack, it creates it sets up a worker queue of processes. So it'll be, say, running 20 RDP clients in parallel, where each of those RDP clients is set up to attack, being ordered to attack a specific occurrence of a specific event. So like the first process that is queued up, its goal is to attack the first message of the sent data. The second process that is queued up is to attack the first message of the received data. The third one is to attack the second message of the sent. So in this way, you're fuzzing all the really deep protocol messages the same amount you're fuzzing the early messages in the protocol. So it's just making sure that you're fuzzing the really deep messages as well in this case. And similarly, you're spending an equal amount of time fuzzing each of the event types. Like if you have an event type that happens 10,000 times versus an event that happens just a couple times, you want to spend an equal amount of time fuzzing those 2 types of events, even though one occurs much more frequently than the other. So I'm going to go really quickly through what a target looks like. Everything is designed to be really quite simple, so there isn't much code actually here, which is good. So for the target, all you have to do is implement initialize routine as well as the breakpoint hit routine for when a breakpoint is hit. In the initialize, you just want to copy the stub that's there, and you want to modify these parameters which indicate which functions and libraries will be considered. The hook exports and hook symbols indicates whether the exports of the library will be considered for hooking, and the symbols, if you enable the symbols, it'll try to download this symbols library from the symbol store and consider hooking each of those symbols that are loaded as well. The libraries just specifies the libraries that will be considered. You can specify them explicitly in that array where you see winsock is being targeted here, or you can specify it by a regex inclusion statement. Similarly for functions, you just specify either the function names explicitly to be considered, or you specify a regex which is an include for the functions to be considered. So that's all it is for initialize. The breakpoint hit is a bit more complicated. For the parameters, first you specify the parameters, which is basically the arguments that are coming in at this breakpoint location. And then you have to give it a calling convention according to the process it's attached to. So in this case, it's a Pascal calling convention, and it needs to be transformed according to the process because it might be a 32 or it might be a 64-bit process which influences the calling convention. And then it transforms it into a registry specification as well as a stack specification. So this is going to make sense in a second, but this basically gives you an arguments structure which has the parsed arguments, and then you can reference the variables naturally. So this is what the parameter specification looks like. In this case, we're hooking winsock send. It does support complex structure types, although this one is a fairly simple structure type. So we have, this is ordered, so make sure to put the arguments in order here. And here the buffer, if you look at the type of the buffer, that means it's a pointer because the type of it is not none. In this case, it's pointing to a method that knows how to parse that specific type. In this case, it's parse the buffer. That buffer is going to be a fixed size buffer, which is according to the argument here size. So if the size variable is 10, you want it to only have a point to a buffer of size 10. So that's handed in through the type args to the reference to the argument. And the fuzz variable you have for each of the variables indicates what the default action is you want to do with that parameter. In all of this case, it's no fuzz for all of them. We only want to fuzz the contents of the buffer. We don't want to be fuzzing the pointer to the buffer, for example, in this case. This is what the parse buffer looks like. It returns just the same format. Can be an array of parameters, but in this case, it just returns. It just searches upwards for the already resolved argument because it needs to look up the size, what the size of this buffer is, and then it just adds it as a field called capital buffer. So here, once you have the parsed arguments, you can just do toString, for example. Then it's going to print all of them. So here you can see the buffer was stored in RDX, and then the contents of the buffer is at that specific address, and you can see the contents of the buffer. It's dumped hex 13 bytes of the buffer there. You can reference each of these fields naturally, like you can do the arguments.buffer. So now that is referring to the pointer to the buffer.toString, and now it's printing out the pointer as well as the contents of the buffer. Or you can go ahead and go right to the buffer itself. You can do arguments.buffer and then dereference the pointer to buffer and toString. So in the line above there, you see it does arguments.size.toInt. So when you reference a parameter like that, you need to convert it to a type. So in this case, you're converting the size to an integer because otherwise it doesn't know what how you want to access that underlying type, for example. So you can access all the arguments really naturally once you have it parsed properly like that. So the process is much simpler, which is great. The only thing you have to change here is in the initialize, just specify the path to exe as well as the command line. You can attach to an existing running process if you include a PID instead, in which case it'll ignore those two arguments and directly attach to an already running process instead. On debugger attach, just use the exact template in the examples, except all you do is specify the targets that are going to be added. You can add multiple targets, but here it's only adding the winsock send to the target list in this case. So the controller is the brains of it. It runs the measurement operation as well as it manages the worker queue of processes which are running the attacks. Here's an example of how you do the measurement instance of the process, the measurement phase. You need to create a breakpoint handler, which the breakpoint handler decides what to do with the fuzz information. In this case, we just want to measure the fuzz blocks, for example. So you just create a breakpoint measurement. You create that process RDP, and then when you tell the controller engine to attach to it, now the RDP process is going to be running with all the instrumentation. So you just wait 5 seconds, you copy the measure out, and then stop it. Now you finish your baseline. So that you took your RDP client, you hook the winsock32 function as it was loaded, and then you connect up to the server, recorded all the communication, waiting 5 seconds, and then terminate. The breakpoint measurement just calls the target breakpoint handler, recording the result. So now we've finished the measurement part of it. For the attack part of it, you just implement a breakpoint attack instead of a breakpoint measurement. The breakpoint attack, you tell it which event name as well as the event number you would like to attack. but you don't need to change any of this normally. You can just use the existing template that's there for controller. So normally you just want to change the target and process implementation. So now I'm going to jump into the first example of fuzzing the XRDP server. So XRDP is an open source RDP server, and I've got it running on a VM right here. So this is the example of the target implementation here. So it's actually, this one is what we've been going through in the example so far. It's targeting winsock32.dll, just the send example. So here we're only hooking the exports of the library. Wrong target. So here I'm running it with a verbose flag. So it's actually connected up to the RDP server here. And so it's just printing the buffers that are being communicated with sent to the RDP server. You can see these later messages here. Look, you don't see any clear text here. It's because they're actually encrypted blobs in this later communication. But if I go up to the earlier communication here, you can see clearly in some of the first messages, you see some clear ASCII. It's connected up to the server. That's my computer name here, for example. So in this case, it is, I just thought I would show you what it looks like printing the buffers before I carry out the attack. Now I'm going to run it with the attack mode. Here we go. And the first thing it does is it's doing a measurement process measurement right now. So it's recording the baseline. So it's printed out that there were 20 messages involved with connecting up to that RDP server, and involved with 257 blocks. All the fuzzable data is decomposed into 8-byte chunks. I'm calling them blocks of fuzzable blocks. Each one of those is considered a fuzz block and fuzzed with some logic. So now I press any key, then it's going to be queuing up. I've got it set up to, I think, run 25 of the RDP clients in parallel right now. Let me go to the controller options. Yeah, so I'm running 25 of them in parallel right now, and they're going to each time out at 5 seconds, and then I'll keep 20 of them running continuously. It usually only takes a matter of probably about 1 minute or so in order to crash the RDP server right now. Right now I'm running the old version, which was vulnerable prior to a few vulnerability disclosures. So you can see here they're attacking all the different events of it right now. Some of the message box are coming up because it's failing to connect because it's fuzzing with some of the early messages and it's causing it to lose connection. So if I give it a few seconds here, I'm hoping we're gonna crash it, and then I'll show you what the crash dump looks like. Come on. Last time I ran it only took about 15 seconds or so. So I'm hoping this is gonna crash in a second. Okay, well, it seems to be taking a little bit longer here than last time, so that's okay, because we're about to show another example in a second, which is going to speed it up a little bit. So back to the example, it still isn't ideal because you see the encrypted messages there deeper in the communication. Although we are fuzzing that data, we may not be fuzzing it properly. We don't know what type of encryption is applied to it. Maybe there's some checksums applied to it as well, for example. So the problem is now we have to figure out, we want to hook it before encryption actually as well. So, and the thing is that we might not know necessarily, say, what encryption protocol is involved there. So I'm just going to be including target, which also prints the symbols along with the sent data. So I'll show you what that other target I've just added looks like. It is this one right here. So all it is doing is explicitly specifying the mst-scax.dll. That's the library responsible for the RDP within the client. And for the functions include statement, it includes everything. So every internal symbol is going to be hooked in this case. and it's only hooking the symbols instead of the exports. And then the breakpoint hit event handler only prints the event name. So then we get an internal view of what it looks like. And I just got to add that right. Oh, I already did. Perfect. Oops. So now this is printing all the internal symbols, but it's also printing the sent data at the same time. So we have a frame of reference. And I'm just going to wait till it connects here. Now, what I'm going to go look at is what's happening just before it sends one of those encrypted messages internally. Whoops. Oh, sorry, guys. Touchy here. There's a message. Okay, so this one here is one of the encrypted blobs that's being sent right here. And you can see just before it, it's calling, say, all these send buffer functions. I originally, when I had a look at it, I thought, maybe let's try to hook, let's have a look at what the parameters are for these send buffers before encryption. You can see here, the encryption function is this RC4, which is being called shortly before the function is called. So these send buffer functions I found actually had really complex very complex definitions, so I wasn't able to easily reverse it. But for the RC4, all you have to do is print, say, define 4 arguments, and they all as pointers to buffers, and then just do print, and then you can clearly see based on the contents of that, it's clear to see which is which. So which argument is which. So that RC4 is the easiest one to hook. So now in this case, now this last target is attacking just that RC4 encrypted data. So here it's just attacking msts.cas.dll, RC4, which this one is a really simple definition, just key size buffer. So now I'm going to go ahead and carry that out for print buffer. So now you can see the data here is looking much better now. You can see mstsc.exe there, and here you can see my local machine time zone, as well as, say, my local IP address as well. So now the data is looking much better. It's looking not encrypted, which is great. So now I'm going to go ahead and carry out that attack using fuzzing the RDP buffers now instead of attacking the WinSock send messages. So again, it does the measurement operation right here. And it found that there were 19 calls to RC4 and corresponding to 150 blocks worth of fuzz data. So now it's carrying out the same process here. And if you look closely at the screen, you might actually I already crashed it now. Okay, so that one was successful. Now it can't connect to the server because it's no longer there. So I'm going to pull up the crash dump to show you what that looks like. Although it's a fixed vulnerability now, which is great. Well, I mean, it could be one of a few. So hopefully this one's patched. Yeah. So this one is the XRDP bitmap compare with CRC. They had a fixed sized array in their bitmap caching, and it's overflown it's gone past the ends of the bounds of the array. And here you can see the self pointer is clearly incorrect. It's just a 4-byte value, BF5F, and it tried to dereference a variable off it, which caused it to crash. This vulnerability has been fixed now, which is great. And okay, that's it for the RDP example. And so I'd be really careful about using say open source software for stuff which might often be connected to the internet. In this case, the XRDP code, if you look at it, there were quite a few pretty bad vulnerabilities in it that can be exploited for remote code execution even before authentication. So you should be really careful about what code you have in your computers which is listening, especially if it's connected to the internet. So this right here was one of the other vulnerabilities where it creates a buffer of just 8 kilobytes, for example, and it doesn't even check when it copies the data into it. So if the client connects and says, oh, the size of the field is actually bigger than that, it'll actually overflow that heap, and that's another really dangerous one. So now the second part of the presentation, I'm going to do a quick demonstration of hooking device I/O control messages. So device I/O control messages are used for low-level communication from user mode up to drivers running the kernel mode. They can be used for things such as low-level disk reading and writing, as an example, but it's used for all sorts of devices and drivers. So you might wonder what kind of devices are communicated with on a normal basis. This is the list of devices that are connected to when you're running Notepad. So if you start up Notepad and you just do file save as and then browse in the file save as dialog that comes up, you browse to say the network locations. This is a list of the devices that are communicated with. Like for example, I don't know what most of these are, to be honest. NSI, Mount Point Manager, LAN-MAN, Datagram Receiver, etc. These ones here you see with these are actually just file system accesses directly here. But NV admin device, I presume that's NVIDIA administration device, for example. So here's a quick example on, I'm not actually going to be attacking the device I/O control messages in this case, and you want to be careful if you do as well, because, for example, if it were a disk write operation, you could be corrupting stuff in your disk as well. So this is here, it's actually just going to be hooking NTDLL, NT device IO control file, which actually, even though it says file in the name, that's actually the lower level device IO control function. Device IO control leads to the device IO control file. And for when the breakpoint hits, it's got more of a complex type here. But again, this isn't a good example for complex structures. None of these are really complex structure in this case. It just says an input buffer, output buffer. Both of them are fixed length buffers, basically. So it's rather simple calling convention. And when this is hit, it's actually just logging it to basically a CSV file, which with the data base 64 encoded, which then we're going to load into Windows Message Analyzer using a parser. So this is just printing the data again. I've got it set up right now to often you might want to increase the surface that it's testing by pairing it, say, with an AutoIt script. In this case, it's using an AutoIt script for each process that attaches to bring up the print dialog as well, to experiment with increasing the surface. So here's what some of the log looks like in terms of who it's communicating with. At the very start, it initializes with NVIDIA admin device with ADVN. I'm not sure what any of this communication is, but that's some of the data it's sending to the NVIDIA admin device. But it's also recording the output buffers as well. So when I ran that there, it was actually saving the data to capture.log here, which if you look at it is basically just a CSV file. And I've written and included a Windows Message Analyzer parser for it. This is kind of what the parser looks like. It's really rather simple. Just the tricky part is the base 64 decoding. And I'm just going to load up that capture file, for example. So right now, the UI has been designed for multiple processes, so you can capture with multiple processes, but in this case we only have Notepad, so you can say expand this, and it's grouped by the device it's communicating with. And each of these, I've separated the input and output buffers into 2 different messages currently, and the decoded data is being right here, for example. So the idea is with Windows, for those of you who aren't familiar with Windows Message Analyzer, I think it was released within the last year by Microsoft. And it's a replacement to the Microsoft Network Monitor tool. So the Windows Message Analyzer is designed to analyze and capture more generic messages, like it can capture and analyze network traffic, for example, but it's more designed for all types of window messages. So it can capture, say, it can process log files and event logs and etc. It's a much more generic than just network captures. It's for all sorts of Windows messages. And although I haven't expanded on it, but you can actually extend this parser to parse the protocol for each of the individual devices that you're communicating with. So now you can write a parser for NVIDIA admin device if you start reverse engineering the protocol of how it's communicating. Okay, and I've just got one last simple example here. So one last example here is, say, writing a sandbox using the framework. Right now it does support things like process forking and etc. But to be honest, I've found the performance isn't quite what I wanted for currently for a sandbox. So you're going to find it's a little bit slow, unfortunately. So in this case, I've written targets to handle several different things. Like it's adding a handles target, which is a resolver for handle identifiers to names, as well as it's adding a target which is identifying what the clean modules are in the application. So by default, currently it's not a really intelligent way of doing it. It assumes the first module loaded is malicious, and any module loaded normally afterwards is considered clean. But if, say, they create a new executable heap, inject into it, that is also considered malicious, so only properly loaded modules are considered clean afterwards. And it's logging registry. And it's logging, this log untrusted is logging the exports of all DLLs only if they're only logging that the function call occurred if it's coming from untrusted code. Because you don't want to see every internal function that's called. You want to see it only if it's coming from untrusted code, for example. And target fork is hooking only the create process function. So when it does a create process function, it will actually fork and attach onto that other process that's being created as well. But the performance isn't quite what I wanted, unfortunately. But I'm working on improvements for that. So here we're running notepad.exe as a quick, simple example. Now I'm just going to bring up the choose font dialog because that'll cause some registry changes as well. But as you can see, it's not the fastest, unfortunately. Just give it a second, sorry. Should be almost there. I've started working on the code in order to upgrade it. Right now it's using the native debugger engine, so it's attaching to each of the processes using the native debugger engine. And in the future, I'd like to upgrade that to be more of to not be actually attaching as a debugger. I want it to be more native-based, not debugger-based, to improve the performance. So I'm just going to close Notepad now. It's embarrassingly slow. Sorry. Come on, you can do it. Well, I guess I don't. There we go.
Is it showing each DLL twice for 32 and 64 bit?
Sorry?
The duplication of DLLs, is it for 32 and 64, or why is it showing hooks twice for each DLL?
You're right. That is coming from each of the targets individually decides whether they want to hook a DLL. So multiple of the targets want to hook each of the DLLs. So one of them decides it wants to hook 0. One of them wants to decide it wants to hook 3 of the exports. So those are from 2 different targets, or why you're seeing duplicates there. Yep. So now that's actually created the this events.log here, which is the log file that recorded for that notepad run. So the registry handler is recording the query values, which are all of those. So this is where Notepad itself is kind of starting up. It's recording that all the export, well, whenever an export of any library is called from untrusted code, it's printing it out here, so you can kind of see what it's doing internally. And you should only be seeing what malicious code is calling. Like if kernel 32 calls ntdll functions, that's automatically filtered out here. And set. Sorry. Yeah, right now it's automatically dereferencing strings at a low level. So this is where, this right here, Common Control Dialog 32, choose font W, that's when I clicked on change the font. So it's been recorded here, and you'll see shortly after it's going to set the values. Yeah, so now it's setting all the registry values as I hit OK, for example. This is changing all the font settings. And here, for example, it's changing it to the Times New Roman as my default font for Notepad. And at the end, it just basically quits. One other thing is I forgot to mention with the vulnerability fuzzing, each time it was creating a process, each process is logging to a file what changes it's made in the connection process, and it's located in this log files folder. So when you have that RDP crash, for example, at the end of my last example, you can go ahead and refer to this log files folder, and you can see how to reproduce the crash, for example. So it's going up sequentially. So the last ones which communicated with it were these bottom ones. So in these log files, you have this one didn't quite reach there. So these last processes, I think, were created, but weren't able to connect to the server, is why we're not seeing any fuzzing. Normally you'd see something like this, where you see the breakpoint handler, you see the arguments are passed in, so if you want to reproduce this attack, you have to create a breakpoint attack sequentially using this seed number to reproduce its fuzzing decisions. And it's telling you that it attacked event 9 of our seed4 buffer. It's fuzzing block 3 from that, name that, from value of this to value of that, for example. So it uses several different algorithms for the changing of the keyword value. So in this case, like it'll either flip a few random bits, or it'll modify a random byte in that keyword, or it'll modify a random word or random D word in that section. So I think that about wraps up my presentation here. Thank you very much for attending, everyone. Yeah.